So let's start. I would like to ask Shubhabrata Das from Presidency University to start this afternoon session with the title Amenable Actions for Groups with Weaker Hyperbolic Properties.
Thank you very much. Thank you for inviting me to give this talk here. It's always a pleasure being at ICTS. So this afternoon, I'll be talking about amenable action. I don't know whether this will interest people in this conference much or not. Amenable action for groups with weaker hyperbolic properties. By that, I mean the groups which are not hyperbolic, but has some features. So this is a joint work with Partho Sarathy Ghosh. And yeah, so I will start by recalling amenability of groups, and then I will go to amenability of group actions, Borel amenable action, and topological amenable action. And we will spend some time about this example, which is amenable action of mapping class group on the boundary of the curve complex, and topological amenable action on this projective measured foliation times the Stone-Check compactification. And then I will briefly talk about some generalizations we could manage to prove. Okay, so amenable groups are generalizations of compact groups or finite groups in particular. So compact groups they admit invariant probability measure. So these are groups which, amenable groups are those which admit invariant mean. Now, what do I mean by means? So this, by mean, I mean that this is an averaging process for bounded functions on the group. So amenable groups are those which admit an invariant mean, which is this map, which says that if you take a bounded function from L infinity is the space of all bounded functions on which G acts this way. This is like convolution, if you want to call it. And you are considering this map, which is a linear map, positive, and takes 1 to 1, and invariant. So this is called an invariant mean. This is also called states, invariant states at some places. Okay, so G is amenable if there exists a G invariant mean on the space of bounded functions L infinity GR. Now, some examples: finite groups are amenable because on finite groups we can average functions like this. This is the usual average. And then abelian groups are also amenable because we can prove by some Markov-Kakutani theorem that on the space of states, these are the space of states, so we can find some fixed point. And that fixed point on the space of states will be the invariant mean that we are looking at. So abelian groups admit a G invariant mean, so they are amenable. Now, these are some other classes of amenable groups: nilpotent groups, polycyclic, solvable, finitely generated groups with sub-exponential growth, etc. And then we can see that by its alternative, these groups, the subgroups in GL and K, they either contain free groups or they are solvable. They have solvable subgroups of finite index, so hence amenable. So either they contain free subgroups or they are amenable. So next, I thought it would be good to give an example of a non-amenable group and why it is non-amenable. Historically, I think this is the reason free groups are not amenable was probably the reason amenability was introduced. And it was introduced in connection with Banach-Tarski paradox, as far as I understand. So why are they not amenable? Suppose there is an invariant mean on F2. We are doing this in particular in the case of free groups with two generators. The general proof will be similar. So suppose we have an invariant mean. Now let us look at the words which start with powers of A. So they are like in the tree, they are like you are looking at the right component, the right-hand side component, which starts with A and powers of A. So then if I consider the set A inverse A, then that will, so by A inverse, applying A inverse, you are canceling the first A, and then you are back at the identity, and then you can have other words as well. So you can write the free group F2 as this union. This is not necessarily disjoint. I mean, this is not disjoint. So we can write F2 as this union. And we are also looking at these sets, which are disjoint. So now I'm looking at A, B times A, that is, you go up and then take a component in the A direction. And then you look at B square times A. That is, you go one step up and then look at the A direction elements. So these are all disjoint sets. This is a tree, so these are all disjoint sets. Now, since we have assumed that there is an invariant mean on F2, now if I start by the definition of mean, so one is the chi of F2, that is one at each point. So that would be less than or equal to, because this, I mean, there could be points in the union which are belonging to both of these sets, right? So then there could be more than, the sum could be 2 as well at points. So the mean would be greater than or equal to this mean. And now you apply the properties of mean and see that it splits, and then you get 2 times the mean of chi A of this set is greater than or equal to half. Then if I apply mean on these sets, which are disjoint, then I see that so these are disjoint sets, and this is not entire F2. So mean of chi F2 would be greater than or equal to this mean. And that splits, and then we get mean of chi A, B times chi A, B square times chi A. But this mean is invariant under the F2 action. So all these are mean of chi A. So we get 3 times this, and that leads us to a contradiction. So this shows that free groups are not amenable. Okay, but free groups, I mean, we will now be looking at free groups as some negatively curved group, and we would like to generalize from this point onward. So amenability, I would also talk about other definitions, because the invariant mean definition would not be the one which is most useful when you are trying to prove something. So this is another definition, another equivalent way of looking at amenability, that the G invariant mean can be looked at as a limit of some G invariant probability, sequence of G invariant probability measures. In the limit, what you get is not a measure, but a mean. So, which gives the following definition. This definition says that a finitely generated group would be amenable if and only if for every epsilon and r. So for any finite, for every epsilon and r, you will have this kind of a probability measure, which is not invariant, but it is almost invariant. So you can make epsilon as small as possible. So it's a finitely supported probability measure, and you translate the measure by the group element, gamma, and the L1 difference, the difference between these two. So this is also a probability measure. Gamma dot mu is also a probability measure. So the L1 difference between them is very small. Now, that, in other words, tells us that G is amenable if and only if there exists an asymptotically G invariant sequence of probability measures, which in the limit, in this sense, would give us the mean. So now we come to amenable action, and amenable action, say, I mean, in a way, so we are looking at, now we are looking at not groups, but group actions on spaces. Firstly, say measure space, space with a quasi-invariant measure on it, and the group acting, and then we also look at some topological version of that. Now, since we are now looking at action and trying to define some version of amenability, it's a dynamical generalization we can think of. And Zimmer observed that many non-amenable groups act similar to amenable groups. In which way, I will make that clear in some time. So here, in case of amenability, we observe that we get a sequence of probability measures, and we can think of the limit giving us a mean. Now, here, you can consider the action of a group G on X, which will have some asymptotically G invariant sequence of probability measures, which is compatible with the group action. I will, in a moment, I will make it clear what I mean by that. So in other words, we can say that we will have a G equivariant section, because here we are looking at the action on X, and for each X element, we are assigning a mean. In other words, for each X element, we are assigning a sequence of probability measure respecting the group action. So by this statement, I mean that there exists a G equivariant section of means on the L infinity GR. So this was the definition. Actually, this is an equivalent definition of Zimmer's definition. This is not the exact one he defined. So this definition tells us that if we are looking at a Borel measure space X nu and G is acting on that, then we call it a Borel amenable action if we find a sequence of probability measures, assignment, so a map mu n, a sequence of maps mu n, which assigns for each element xi in capital X, a sequence of probability measures in G. And this assignment follows this condition. And what is it saying? It is saying that it can so happen that this difference for some large n of n is not equal to 0. That means this map is not equivariant, but in the limit as n goes to 0 for almost every x in capital X, this limit vanishes. That means this is up to measure nu, this assignment is equivariant in the limit. So this is asymptotic equivariance, we can say. This sequence of maps are asymptotically equivariant. So Zimmer defined this amenable action. This assignment was only required to be Borel maps, via Borel maps. So we call this Borel amenability. Now, Anantaraman Delaroche extended this notion of amenable action to topological setting. And she defined the same definition essentially, but we are not asking this limit expression to vanish only for full measure set. I mean, we are not allowing any point to behave otherwise, for any sequence of assignments of probability measure to behave otherwise, to not become 0. So here, it's the limit supremum that goes to 0 as n goes to infinity. Otherwise, the assignment is similar. So here we have a few remarks. We can easily see from this that if I take x to be a point, then I have a sequence of probability measure assignments, right? And that satisfies this expression. And that means I have amenability. So if the group action satisfies this expression in 2, then and x is a point, then it is an amenable group. So so they admit a topological action, topologically amenable action on a point, amenable groups. We can look at them that way. So in this sense, it's a generalization. From a point, we are generalizing to compact sets. And then stabilizer, so if we have an action like this, the stabilizer of a point has to be amenable. Just restatement of this first observation. And the third thing is amenable action now becomes interesting only in the case of non-amenable groups, this Borel and topological amenable action. Okay, so this is something I just wanted to mention. I won't be giving definition or anything about these. So this is another very useful description of amenable groups, which says that the C-star algebra, reduced C-star algebra of these groups are nuclear. So this is some property of a C-star algebra. Now, Ozawa proved, so this is about amenable groups. About amenable action, Narutaka Ozawa in 2006 proved that topologically amenable action would be equivalent to having a reduced C-star algebra which is exact. Means if we take an exact sequence of C-star algebras and do a tensor product, that sequence remains exact. So this is a useful equivalence of this definition of amenable action. And using that, one can show that if a group satisfies, if a group admits an amenable action, it satisfies these conjectures. Anyway, now earlier we proved that free groups are not amenable, but here, as a first example, I'm trying to show that free groups are topologically amenable. They are kind of the first example of a non-amenable group, but they are also the first example of a group which admits amenable action. So what do I mean by that? And where does it act amenably? So the free group, we look at the Gromov boundary of the free group, which is the equivalence class of rays, geodesic rays starting from E. Here we can take all the rays starting from E, and that will give us the Gromov boundary, this being a tree. So this is a compact space under a certain topology. Here we can even give a metric. So this is a picture of the free group and the boundary. And here we have an assignment of probability measures for points in the free group boundary. Now, what do I do here? This example will be a very suggestive one, because in all the further generalizations of this fact, this is essentially what we would be doing. We will have this example in the back of our mind. So what is happening here? What is the assignment? We take a point in the boundary. We have a unique geodesic ray starting from identity. And what we do is we need to, for this point, we need to assign a sequence of probability measures. What we do is we take this geodesic ray and assign uniform probability measure to the first n length segment. And we increase the number of points as we go along with the geodesic, and the uniform probability measure, the charges that we are assigning to each point, they are going to 0. But that's still a probability measure, finitely supported probability measure. And that is the assignment that we are making here. Now we can easily see that if this is the assignment of probability, what is happening to the probability measure when I'm acting it by a group element. So when I'm looking at this measure, this is for the point S dot X, where S is coming from the free group. So if X is a point in the boundary, S dot X is some other point in the boundary. And that point also has a unique geodesic starting, connecting to that point, connecting identity to that point. So for this probability measure, we will assign uniform probability sequence of uniform probability measures along the geodesic ray that goes to the point S dot X. Now, about this probability measure, mu X, we are acting the measure by S. And this is like a convolution. We are just shifting the point on which the measure acts by S inverse, and then applying the map mu nx, the probability measure, which is an L1 function. So we are now looking at the difference between these two probability measures in L1 norm, and that difference turns out to be this, which is bounded in the numerator. The denominator increases and it goes to 0. So we get topological amenability with this assignment of probability measures for each point on the boundary. Now, this assignment is a little suggestive what we would like to do in the further cases. Now, the next example would be of hyperbolic groups. For hyperbolic, hyperbolic groups are generalizations of free groups, and geodesic metric space would be hyperbolic if all geodesic triangles would be delta slim for some uniform delta, which means that if I take a delta neighborhood of 2 of its sides, the third side will be contained in the union of those delta neighborhoods. And a group would be called hyperbolic if it acts geometrically on a proper hyperbolic metric space. This guarantees the group is finitely generated. And so equivalently, a group would be hyperbolic if for some generating set, the Cayley graph is a delta hyperbolic metric space, like this. So in this case also, we can define a boundary at infinity, which will be a compact topological space. The definition of boundary remains the same. We consider geodesic rays, and the equivalence relation here we put is they are asymptotic. That means they remain closed, uniformly closed for all time. In case of free groups, we did not have to mention this because they are the same. They're starting from identity, and because we have unique geodesics, they are same. So here we add this condition to identify geodesics, because their long-term behaviors are the same. They're going to the same point in the boundary. So this is a compact space. We have assumed a proper hyperbolic metric space with a suitable topology. Now, hyperbolic groups are also topologically amenable. So like free groups, in this case also, we would assign probability measures for boundary points, and the assignment would be similar. In case of free groups, we had a unique geodesic ray joining identity to the boundary point, and we charged only the first n segment for the nth assignment with a uniform probability measure. In this case, we do not have a unique geodesic going to the point in the boundary starting from identity. We have many geodesic rays by under this definition. So there are any given point in the boundary would correspond to several geodesic rays. So in this case, the choice of the set that we are going to assign a probability measure is a little more complicated. So how do we charge this? The proof is quite similar. What we do is we define a cylinder-like set, which is in this picture, this one. So this is the one which goes to Gx. The black one goes to Gx. This black cylinder is the set that we are going to assign a uniform probability measure to. And this red cylinder is what happens if I translate this one with if I translate the probability measure that I had assigned to the point, to the geodesic cylinder, which goes to the point X at boundary, if I translate it with the group element small g, then it goes to this. So now how are these two cylinders going to behave so that their difference in the, as we had mentioned in this equation, in this expression. So we want an assignment which satisfies this. So here we would like to find a suitable set, which is like a cylinder, and this cylinder is obtained as, so we take a geodesic ray that goes to the boundary point, and then we take a cylinder of some suitable radius Rn around it, and we take a 2K length segment of that cylinder, portion of that cylinder. And since the group is finitely generated here, so this will have finitely many elements, and we can define a uniform probability measure again on this set. So, and this set satisfies this these relations with respect to its translates. And now we define a mapping which goes from the boundary of the hyperbolic group to the probability measures supported on the hyperbolic group. And the assignment that we give is this. We take these cylinders we constructed here, and we take the characteristic function on those cylinders, and we divide it by the finite size of that cylinder. So this gives us a probability measure which is the nth assignment to the boundary point X. This is identity, this is the boundary point X. So we can show that with this assignment, this map will satisfy the condition 2 that we had mentioned earlier in the definition of topological amenability. And it will give hyperbolic groups to be topologically amenable. Okay, so now little survey on boundary amenability. This is called boundary amenability because in most of these cases, we are getting the topological amenable action on the boundary. And Ozawa proved that relatively hyperbolic groups, which are generalizations of hyperbolic groups. So these groups are not hyperbolic themselves, but they are hyperbolic modulo some subgroups. If you quotient out certain subgroups in these groups geometrically, if you cone them off in a certain sense, then the resulting graph should be hyperbolic. And they should satisfy some extra conditions along with, which is called fineness, defined by Bowditch. So relatively hyperbolic groups are generalizations of hyperbolic groups, which also admit a topological amenable action. Like hyperbolic groups, relatively hyperbolic groups also admit a boundary at infinity, which is called the Bowditch boundary. And the Bowditch bound, so in general, relatively hyperbolic groups do not admit topological amenable action on the Bowditch boundary like the hyperbolic groups. Because in case of hyperbolic group, we know how the subgroups are going to be. And so there are examples of groups which are not topologically amenable. So we mentioned that topological amenability is equivalent to being exact, the reduced sister algebra being exact. And there are constructions by Gromov, which is a group which is not exact. So it does not embed in Hilbert spaces and all. These are non-exact groups. So in particular, if we take, say, two non-exact groups, and we take a free product of them, that free product is going to be a relatively hyperbolic group, modulo the vertex groups. And this relatively hyperbolic group will have a non-trivial boundary, which is the Bowditch boundary. Now we mentioned in case of topological amenable action that point stabilizers should be amenable. So even if we take, say, two non-exact groups and their free product, The stabilizers for the parabolic points, which correspond to these vertex groups, they are going to be non-exact. So that is kind of an obstruction. So relatively hyperbolic groups are boundary amenable, but not on their Bowditch boundary. They are only if all the parabolic subgroups are amenable. With all amenable parabolic subgroups, they will admit topological amenable action on the Bowditch boundary. Otherwise, we need to take a product with some Stonecheck compactification in case the parabolic subgroups are exact. Okay, so that is Ozawa's theorem. Ida and Hamenstad proved that mapping class groups of surfaces, non-exceptional surfaces, say, are boundary amenable. So their proofs are quite different. Hamenstad's proof, she proves it on the something called complete geodesic laminations and boundary amenability on the space of such objects. Kida proves it on the boundary of curve complex. So I will be spending some time about the proof of Kida. Hamenstad's proof I will not be discussing here, but this is a result at a similar time, and mapping class groups are boundary topologically amenable. And also recently, Bestvina, Girardel, and Horbes proved that out-FNs are boundary amenable. Their proof follows the argument in Kida to a large extent. Okay, so boundary amenability of mapping class groups. I have recalled a few definitions which would be useful here to talk about the remaining proof of outline of the proof of Kida. So these are compact orientable surfaces with complexity greater than 0. And these are the mapping class groups. Gamma is the mapping class group. C is the curve complex. And S is the set of, V is the set of vertices, which are the non-peripheral, non-trivial curves, which are simply, which are not self-intersecting. So we take them as vertices and we add edges if they are disjoint, and we can take a we can take a set of such curves, and if they are all disjoint, we can throw in simplices for them. So that defines the set of simplices on the curve complex, and this can be seen easily that the mapping class group would be acting on this complex of curves isometrically. The metric is induced by the combinatorial metric. And if the complexity is greater than 0, the dimension of the curve complex would be kappa of the surface, sigma. But the curve complex is locally infinite. It's not a proper hyperbolic metric space. And that is the main point of difficulty that we have, and why I am describing the proof of Kida in some detail is that this is the strategy that is followed, that will be followed in most of the further proofs, where the group is acting on a hyperbolic metric space, but essentially a non-proper hyperbolic metric space, where we do not have a compact boundary. So these are few results, which the most important is the hyperbolicity of the curve complex, which was a result by Mazur and Minsky, that the curve complex of suitable surface, these kind of surfaces, is Gromov hyperbolic as a metric space. And the group action that the mapping class group has on this is it induces an action on the boundary, the Gromov boundary of the curve complex. So here, this is a metrizable space, but it is not compact. It's not compact here. So because this is not a proper hyperbolic metric space. So now we look at another object which I think have been discussed in this conference quite a lot, and I am just mentioning this for the sake of, I mean, because we may use these terms in the coming slides. So this is the geometric intersection number between simple closed curves, and by this we mean these functions defined on the vertex set of the curve complex, which are non-negative, and by this PR sigma, we mean the projectivization of that. We quotient out all the functions by action of our positive real numbers here. So so these are kind of function spaces on the vertex set of the curve complex. Here now I consider this embedding. I embed the vertex set of the curve complex inside this function space, and then I have a quotient map from this space R sigma to PR sigma. So I get an embedding from the vertex set of the curve complex inside PR sigma. So the definition of MF sigma, the measured foliation, is that you consider all, so you consider the elements alpha from the vertex set here, consider all their multiples lambda alpha. Now this via this embedding it lies here, and you take the closure of that set here with this topology. Now the projective measured foliation, the PMF, would be you go one step further, you look at it here and you close it here. So that is PMF, it's the set of projective measured foliations. It's also called the Thurston boundary. And these sets are identified with these objects. So here the most important, interesting thing is to note that this is a compact space, and here this is like the closed unit disk, closed unit ball in this dimension. Now, gamma also acts on this space of projective measured foliations, and the elements in gamma are classified via the fixed points they have in the space. And here we have this theorem due to McCarthy and Papadopoulos, which says that there are non-amenable stabilizers under this action. Even though this is a compact space, we cannot expect a topologically amenable action on this of gamma on this space, because we have non-amenable stabilizers. Because we had seen earlier that stabilizers must be amenable under a topological amenable action. So the action of gamma on the projective measured foliations is not topologically amenable. But we want to show boundary amenability for mapping class groups. So now we are looking at another action of gamma on the induced action on the Gromov boundary of the curve complex. Now, what do I mean by that? So what is this set also? So if we take a foliation, projective measured foliation, an element from PMF, I can define this, this intersection number for this foliation as well. I can extend it there. I can also extend it to MF cross MF. So this is a transverse measure, I mean, coming from the foliation. And this is the set of minimal laminations, minimal foliations in this collection, which are, I mean, any element in the vertex set, that means any simple closed curve will have a positive intersection with these element F in the foliation. So this is the set of minimal measured foliation, if we may say. Now, if we take two elements from this set, they are called topologically equivalent if the intersection number is 0. Yes. Sorry, the vertex set. So now, if we take two such elements from this set min, we say that the two elements are topologically equivalent if the intersection number is 0. Now, it was a result by Erika Clarick. She described the boundary of the curve complex, and she described this as the space of all minimal topological foliations. This is the minimal measured foliation, this is the minimal topological foliation, and this space is described as the quotient of this space under this equivalence relation. So we can see that there is a map from this space to this space, which is a continuous closed, and each pre-image of a point here is a compact set in min. And this has a Borel section. That means there is a set inside min to which this is identified, the delta C, and that shows that delta C can be seen as a standard Borel space. And then we have the theorem by Kida, which says that if sigma is a compact orientable surface with complexity positive, and mu is a gamma quasi-invariant probability measure on this boundary, then the action here, by amenable I mean Borel amenable, then this action of the mapping class group on the boundary with this quasi-invariant measure is Borel amenable. So that's the first part of the result by Kida. And here I have added a little sketch of the proof. Now here we come to the same difficulty. In case of relatively hyperbolic group, the graph that the group was acting on was not non-proper, but it was not uniformly proper. Here I have an action on a hyperbolic graph which is non-proper. So the boundary is not compact. Now, also to define the measures, earlier I used the properness because the sets that I considered, they were finite sets, and I could charge them with a uniform probability measure. That's not the same thing I can do on these sets, and I can have a sequence of such probability measures. So even though C is hyperbolic, it's not locally finite, but there is another version of local finiteness that one can obtain using tight geodesics, which were defined by Bowditch, I believe. So tight geodesics I am not going to define. So this is it's a good class of geodesics that exists between any two points in the curve complex. And so this is the set of geodesics. This is the set of tight geodesics. You mean the tight geodesic? I do not know exactly definition of tight geodesic in other setting, but I mean, we also have looked at an action on these things called projection complexes. There you have something called a standard path, which resembles tight geodesics in the curve complex. So this is the set of all geodesics. This is the set of all tight geodesics. And this is a result, I think, by Bowditch, that this set is non-empty. And here we are looking at a little variation of the set of tight geodesics. We are looking at the union of all these sets. This is a set joining x, y, tight geodesics joining x and y. So here I am looking at the union of all LT x prime, y prime, where x prime ranges over this ball and y prime ranges over this ball. So it's like a little variation. It's like looking at a cylinder of tight geodesics between these two ends. So now the curve complex C has some uniform local finiteness property with respect to these tight geodesics. I'm not going to go into the detail of what I mean by uniform local finiteness, but this is the condition which is enough to guarantee a similar situation that I had in case of a proper hyperbolic metric space, an action on a proper hyperbolic metric space. So with respect to tight geodesics, I am in a similar situation. So now Kida looked at these sets. It may look a little complicated. So it's better if we look at from the end. So we want some function to be defined on the Gromov boundary of the curve complex into the probability measure supported on the. So here we are looking at the curve complex. So if we want to have such probability measures, what we are doing is we are defining this map to be image of this map. Now, how do I get this map? I get this map like this. And what is this? So this set is defined as the characteristic function, sorry, this function is defined as the characteristic function of this set. Now, what is this set? This set says that if I take alpha in the set, in this set, this cylinder of tight geodesics, if I take an alpha, and then I take this segment of alpha, which is the n to twice n. This segment, n length segment of alpha, I collect for all elements from this cylinder. So in a sense, you can say that this set is a cross section of this cylinder. Like earlier, we were looking at some cross section of cylinders in the hyperbolic metric space when we were proving the topological amenability for the hyperbolic groups. We were looking at some section, some portion of a cylinder. Here too, Kida looked at a portion of a cylinder, and that cylinder is given by the tight geodesics. And because of this uniform local finiteness, this set has a finite size. So he defines this function, and this function is you kind of average them in a certain way. And this assignment gives us the things that we require. So I have kind of, have put many things under the carpet here. Tried to make it look similar to the definition I have given. But there are many things here which I am not mentioning. But essentially what goes on is this, that you define these functions like this, and they have L1 norm 1. We can look at them as probability measures. And they satisfy some asymptotic, they are invariant under this G action, and they satisfy this. These two things put together, we can think of some asymptotic equivariance of these assignments. Now, I define this function sigma n from the boundary of the curve complex into the probability measures on this curve complex. And this is my assignment. Now, if you remember the heuristic, the way to look at amenable action I mentioned earlier, that we can think of it as a section, as an equivariant section on the set we are trying to define these maps on. So these are the probability measures that we are assigning, and they will in some sense converge to an invariant measurable system of means. So these means, this is a function, this is not one mean, this is a family of means, this is a section. This assigns for each point xi in this boundary, it assigns a min. Now, these probability measures are in some sense converging to those means pointwise. So I won't go into the detail of this proof further because this will not serve the purpose of this talk. I mentioned this proof in this detail because it helps us see that what happens, how can we avoid the difficulty that we come across when the space is not locally finite. So this is a good example. Here, Kida has obtained this by considering tight geodesics. I wanted to mention that. So now the proof is completed using co-compactness of the action of the mapping class group on this curve complex. I won't go into the detail of that. So I will just briefly mention that these groups are also exact. That means they are also topologically amenable, mapping class groups. Now, how do we get topological amenability? Because here this leads us to the Borel amenability, but not topological amenability so far. But using some result of Ozawa, Kida was able to show topological amenability for mapping class groups as well. This result says that if a group acts, so here look at this space Y as an auxiliary space, just in case your stabilizers are not good. So you take a product with these spaces Y. These are also compact spaces. These are typically the Stone-Check compactifications if we need them at all. So Ozawa's result says that if G is acting on metric spaces X and Y, sorry, not metric spaces, compact topological spaces X and Y, and K is a countable graph. Now, if I have Borel maps from X to prob K, which satisfies the same condition as in topological amenability, and if the stabilizers for points in this countable graph, they are all topologically amenable, then the group, because you see here the action is a Borel amenable action. Now he's claiming that the group G has topological amenable action on a product of X and Y. So this Y you require only if these are all topologically amenable but not amenable, because the action has to be, stabilizers have to be amenable for a topological amenable action. Anyway, so here is a brief outline of the proof of topological amenability, which says that Borel maps, we had a sequence of Borel maps on delta of the curve boundary of the curve complex. Now we also have seen that there is a quotient map from min to the topological minimal foliations. And this is an equivariant continuous map. So what we do is we compose them. Now, we had a map from delta C to prob of the vertex set of curve complex. We compose these two, we get a map from min to prob VC. And we also have another equivariant, not asymptotically equivariant or anything. We have an equivariant map, equivariant Borel map on the complement of this set. So here on this set, we have a sequence of maps like these, which are asymptotically equivariant. And here we have an equivariant map. What we are doing is we are just composing them in a certain way. We are just composing them, and we get a map from P. We are adding them because on this set we have a map. On this set we have a map. If we take the sum of these two maps, say on the union set, then we have asymptotic equivariance, because on one set we have asymptotic equivariance, on one set we have equivariance. So we get these maps, and the stabilizers of these simplices can also be shown to be topologically amenable. And then by using Ozawa's result, Kida was able to show that mapping class group acts on this product. This is a compact space, this is a compact space, on this compact space, topologically amenably. So this is Kida's proof. Now I will briefly talk about some generalizations which are acylindrically hyperbolic groups. And mapping class group is one example of acylindrically hyperbolic group, because while looking at the mapping class group action on the curve complex, Bowditch observed that in this action, these long cylinders are essentially fixed. So what is an acylindrically hyperbolic group? It acts acylindrically on a hyperbolic metric space without essentially without essentially fixing long cylinders. So essentially, long cylinders are all moved. The set that fixes it or coarsely fixes it is finite. So these are some elements, loxodromic elements, when the orbit map is QI embedded. And WPD, an element, loxodromic element is called WPD if it satisfies some weak proper discontinuity, some weaker version of proper discontinuous action. And acylindrically hyperbolic groups, it's sort of clear from the definition, they will have WPD elements. Now, Bowditch showed that the mapping class group action on the curve complex is acylindrical and the pseudo-Anosov elements are WPD elements. So here I will talk briefly about random walks on acylindrically hyperbolic groups. A random walk is you take a group, you consider a probability measure on the group, and then you start a walk which is like you consider random elements with this measure, and then you keep multiplying them, and then you will have a random trajectory. And that random trajectory is going to converge in a certain sense to some boundary, which is a measure space. Now, what I look at here is, I look at the action of a group on a suitable hyperbolic metric space with WPD element or more particularly acylindrical action. So I look at the orbit map. I look at a random walk and look at the orbit map that pushes the random walk into the hyperbolic metric space. So remember that this is essentially not a proper hyperbolic metric space. So it has a boundary, the Gromov boundary, but it is not compact. This is a result by Mehar and Teodzo, which says that if G acts on a hyperbolic space with a suitable generating probability measure, with suitable conditions on the measure, then if the action is either acylindrical or it has a WPD element in the support of mu, the measure mu, then the random walk on X, I mean, that you get by transferring the random walk on G to X, there is a mu stationary probability measure on the boundary of the hyperbolic metric space, such that the boundary, the geometric boundary delta X with this mu stationary probability, this is a harmonic measure. So this is a hitting measure of the random walk on the hyperbolic space X. So what you can say is that this geometric boundary with this measure is the Poisson boundary of this group. So this is a result by Mehar and Teodzo. Now we use this result to prove Borel amenable action for such groups on this boundary. And so the thing that we do here is we make use of some finiteness condition like the tight geodesics Kira had in the mapping class group curve complex situation. So these conditions are very similar to the Mehar-Teodzo result. So we take those same things as our hypothesis, and then we say that this action is Borel amenable. In particular, if the group is acylindrical, it's acting acylindrically on X, then also we have a Borel amenable action. This is a little more general. So, I mean, quick sketch of the proof is we are essentially trying to do the same thing we had done earlier, we had seen earlier, but here the situation is, I mean, like curve complex is a very nice object. You have a lot of information on the curve complex. Here you have just a hyperbolic metric space, and that too it is not proper. So you essentially do not know much about the action of the group on the hyperbolic space, like you knew in the case of you had a result by Bowditch and other results like Clarik's result, etc. So here you do not know much about the boundary, much about the hyperbolic space and the boundary. So what we did here is we looked at the shadow in terms of this. We are assuming that we have a WPD element, and in terms of that, the shadow is nothing but you take a light source here, you take a ball here, and you look at all the geodesics that are emanating from alpha passing through the ball. So they will end up here. So this is the shadow of this ball with the light source at alpha. So this is the shadow, definition of shadow, and F alpha beta is the collection of all geodesics joining alpha to beta. And here we made use of some elements that were defined in the work of Meher and Teodzo, which are called the bounded geometry elements. And the bounded geometry elements, if you see the definition, it says that, I mean, you are looking at bounded geometry element with respect to alpha and beta. They are ideal points. They are in the boundary. But you are considering those group elements such that alpha would belong to the shadow of this ball with respect to the light source here, and beta would belong to the, you take this point to, you now look at a ball around this point and put the light source here at the other point. So you collect all the group elements which behave like this in terms of alpha and beta. These are the elements that you call the bounded geometry elements. And so why are we considering these elements? Now, the way tight geodesics were giving some uniform local finiteness in the case of curve complex, these elements are going to give us some local finiteness. So we are going to charge not arbitrary points in this metric space, but the bounded geometry elements in this metric space. And using that, we are trying to prove the amenable action. So this set is, you are taking one side of this, you are looking at the shadow. So here, suppose you have alpha here, so you are looking at the shadow of alpha somewhere here with respect to this ball. And now you are taking all the bounded geometry elements for all betas that lie here. So that is essentially the set that we are defining here. So these are kind of the points that we have in this set. We are going to charge these points, I mean, some segments of these points. So one important thing is that this funnel grows linearly. And what I mean is this, and we charge only a finite set if we restrict it in some interval. So we again define sets very similar to the hyperbolic situation and the mapping class group situation. And even in the relatively hyperbolic situation, similar sets were charged. And by charge, I mean assigning uniform probability measure on the elements in that set. And these sets behave like this. So if I translate them, and so they follow these containments. And then so this is the uniform probability measure, just like I mentioned earlier. So we consider these sets and we consider uniform probability measures. And we now here for this, we take one further round of average, I mean, kind of a Cesaro mean of these things. So now if we have, so now this is coming from the hypothesis that if we have a G action on hyperbolic space, and these are points from X, and alpha is coming from the boundary, then it is a very similar kind of estimate in the mapping class group curve complex situation we observed in terms of the function H. And now we fix this first coordinate, and we define these maps, these probability measures. So by fixing this. So they also satisfy this. And finally, so finally we have the asymptotic equivariance. And that proves the Borel amenability for such groups, such group actions on the boundary of the hyperbolic space. They are acting acylindrically or with WPT elements. So essentially, we made use of the construction that Meher and Teodzo did. So here we could also prove a similar result for hierarchically hyperbolic groups, and these are groups. I will not go into the definition. Certainly, there are a lot of things in the definition. So essentially, what it has is an indexing set, which is called hierarchy. I mean, which we are calling hierarchy. That is an indexing set and a collection of hyperbolic graphs, and indexed by this hierarchy set, and certain collection of projection maps. So this entire thing, this data put together, satisfying some axioms, is called a hierarchically hyperbolic space. So there are many axioms that they satisfy. Some 10 axioms, I believe. So so a hierarchically hyperbolic group is a finitely generated group, and G is a hierarchy on this Cayley graph. And I mean, this pair, I mean, a finitely generated group with this hierarchy on the Cayley graph would be called a hierarchically hyperbolic group if it acts. So this is a hyperbolic Cayley graph on which you have this hierarchy, and they satisfy all these axioms that I haven't mentioned. So the group will be acting on this hierarchically hyperbolic space, I mean, via structure preserving automorphisms, which preserves this hierarchical structure. So now, so there is a boundary that is defined for such groups, hierarchically hyperbolic groups, by Durham, Hagen, and Sisto, and this boundary, in some sense, can be thought of as a convex combination of the Gromov boundaries that you get from this collection. So we could define. So essentially, this definition would be like a gluing of various topological amenable actions that you are getting from the components of this contact graphs and so on. So the result here is that if you have a hierarchically hyperbolic group, okay, I didn't hear a bell, so I thought it was not yet the time. Sorry, I am over time already. So hierarchically hyperbolic groups act on the hierarchical boundary topologically amenably, and as a corollary, this gives a different proof of mapping class groups to be topologically amenable. Thank you. No, it's not on the projective measured foliation. It is Borel amenable, but not topologically amenable. Okay, I do not know about these things.